Hello students, we discuss today Raman spectroscopy. Raman spectroscopy. When that beam of light is incident on any liquid sample, then scattering of that incident light takes place, and that scattered light consists of different type of wavelengths. That scattered light consists of different type of wavelengths. That's some scattered light consists of wavelengths same as that of incident beam, incident light. Such type of scattering is known as Raman scattering, and some light radiations, scattered light radiations, consist of wavelengths different than that of incident beam. That type of scattering is known as Raman scattering. And this is Raman effect of Raman scattering. Then that scattered Raman scattering or Raman spectrum, that Raman spectrum is nothing but those scattered wavelengths having wavelength different than that of incident beam, incident light. Then that is nothing but Raman spectrum. That Raman spectrum consists, that is that scattered radiations consist, that scattered radiations is considered here as a Raman spectrum, and that scattered radiation, that is Raman spectrum, consists of three type of wavelengths. First, that is same as that of incident beam. Then second type, wavelength less than that of incident beam. And third, wavelength greater than that of incident beam. These three group of lines, group of scattered lines, that are known as Raman spectrum. That is nothing but Raman spectrum. That scattering always takes place with decrease in intensity of incident beam. Decrease in intensity of incident beam. That is that group of all three type of scattered light rays that total have less intensity than that of incident beam, because that intensity is scattered, and therefore intensity of that scattered radiations is always less than that of intensity of incident light radiation. Then if we consider, depending on wavelength of scattered light, that scattered light, that three type of wavelengths, same, more and less wavelength than incident. Depending on that wavelength of scattered radiations, that scattered radiations are divided into three types. First type is group of lines having same same wavelength as that of incident light, that is lambda s is equal to lambda I. Lambda s is wavelength of scattered light and lambda I is wavelength of incident light. That lambda s is equal to lambda I. That wavelength is highest intensity, and that light radiation is observed as a middle line of Raman spectrum. Then second group is a group of lines having less wavelength than incident radiations. That is lambda s is less than lambda I. Group of these lines are called anti-Stokes lines, and that first group, which is same wavelength, that is known that line is known as Rayleigh lines or Rayleigh scattering or Rayleigh line. And here having wavelength less than that of incident radiation, that one is known as anti-Stokes line. And third group of lines with wavelength greater than that of incident, that one is known as Stokes lines. Thus here, depending on that, with increase in wavelength, that middle high intensity, which one is shown by dark line, high intensity line having wavelength that is incident and scattered, that is lambda s and lambda I, same wavelength, then that first anti-Stokes line wavelength is less than that of incident, and Stokes line wavelength is greater than incident. That anti-Stokes lines that have very small intensity, therefore that one is shown here as a small height. Then that Stokes, which one is intermediate intensity, and that anti-Stokes that Rayleigh, which is high intensity, which one is shown dark. So anti-Stokes less intensity, Stokes middle, and Rayleigh high intensity. Then consider Stokes lines. Consider Stokes line, or consider here first anti-Stokes line. We consider first anti-Stokes line. Here for anti-Stokes lines, wavelength of scattered is less than wavelength of incident. Here wavelength of scattered is less than wavelength of incident. Wavelength decreases here. Wavelength decreases. Means if we consider frequency, and we know that frequency and wavelength are inversely related. Means for anti-Stokes, wavelength is less. Means here frequency is greater than that of incident. Frequency means energy also. Frequency and energy again directly proportional. Therefore, for anti-Stokes, wavelength is less than that of incident, but frequency and energy is higher than that of, more than that of incident beam, incident light. Means here that beam of radiation, that is anti-Stokes line, is more energetic than that of incident light. Then from where that energy, excess energy, where that radiation light obtained? That is means here anti-Stokes lines are produced because of transfer of energy from that sample to radiation, from sample to radiation during the scattering. Energy transfer from that matter or that sample to radiation. Therefore, energy of radiation increases. Hence, wavelength decreases. Energy increases. Hence, due to this type of due to emission of or due to such type of scattering, energy of matter, energy of sample decreases. And here, if we consider for anti-Stokes line, that um, value of that Raman shift, value of Raman shift. Raman shift is nothing but frequency of incident light minus frequency of scattered light. Frequency of mu s minus mu I. It means that incident minus scattered, that is nothing but Raman shift. That one is frequency of incident minus frequency of scattered. Hence, for scattered, for anti-Stokes line, that frequency of scattered is increases. Scattered light is more frequency. Therefore, incident minus frequency of incidence minus scattered, that will be negative. Hence, for anti-Stokes lines, Raman shift will be negative. Raman shift will be negative. Then, if we consider that Stokes lines. For Stokes lines, what is wavelength situation? Wavelength is greater than scattered light is greater than wavelength of incident light. Hence, frequency of scattered is less than that of frequency of incident. Means energy is also less for scattered than incident. Means during scattering, energy of that radiation decreases. Means energy of radiation decreases means energy transfer from radiation to matter. And or sample, and therefore energy of that sample or matter increases because of Stokes lines, because of such type of scattering, that is Stokes lines. And since here frequency decreases, frequency of that scattered light less than that of frequency of incident light, therefore Raman shift for Stokes lines, that is value of delta mu, which is nothing but frequency of incident minus frequency of scattered, mu I minus mu S. Scattered less frequency, less energy. Therefore, than that of incident. Therefore, for Stokes lines, Raman shift is positive. Remember that. For Stokes lines, Raman shift is positive. Means how that Stokes lines produced and how that anti-Stokes lines produced. Anti-Stokes lines produced because of transfer of energy from matter to radiation. Matter to radiation. And how that of Stokes line produced? Stokes line produced because of transfer of energy from radiation to matter. Radiation to matter. Out of these two situations, first situation, that is the energy transfer from radiation, that matter to radiation, anti-Stokes. That one is a rare situation, and therefore that intensity of anti-Stokes lines is less than that of intensity of Stokes lines. This one is more probably takes place. That is for Stokes lines, energy transfer from matter to radiation. This one is more probably takes place. Therefore, okay, this one is about that Stokes lines, anti-Stokes lines, and Rayleigh lines. This one about that Raman Raman scattering. Then we discuss here quantum theory of Raman scattering. Quantum theory of Raman scattering, which one is many times asked for 3 marks joint question. That is, what is Raman scattering, and discuss the theory of quantum theory of Raman scattering as like this. Then quantum theory of Raman spectra is based on theory of conservation of energy. Theory of conservation of energy. What is conservation of energy? That is energy neither created nor destroyed. One form of energy only converted into another form. This one is the energy conservation. Then this quantum theory of Raman spectra is based on this theory of conservation of energy. Then consider energy of radiation before scattering is h mu I. Energy of radiation before scattering, h mu I. Energy of radiation after scattering, h mu S. And energy of matter before scattering, E1. Energy of matter after scattering, E2. Then according to theory of that energy conservation theory, we can write total energy of matter and radiation. Total energy of matter and radiation before scattering is the same as that of total energy of matter and radiation after scattering. This is written as per energy conservation law. That is, energy of matter and radiation before scattering is equal to energy of matter and radiation after scattering. That is, E1 plus h mu I is equal to E2 plus h mu S. Therefore, rearrange h mu I minus h mu S is equal to E2 minus E1. E2 minus E1 delta E. And that if we consider H common, then mu I minus mu S, that is nothing but Raman shift. Frequency of incident minus frequency of scattered light. That is Raman shift. Therefore, this equation become delta E. Delta E is equal to change in energy. Delta E is equal to H mu delta, H delta mu. That delta mu is Raman shift. Then in wave number form, same equation we can write as a delta E is equal to HC into delta mu bar. Delta mu bar. By using this equation, we can calculate Raman shift for from Raman spectrum. Then Raman shift is discussed here. This one is only for that theory of quantum theory of Raman spectra. Which one is for 3 marks? This equation and that symbols are important here, and the energy conservation equation. Then Raman shift. That Raman shift is nothing but difference between incident frequency and scattered frequency. That is delta mu is frequency of incident minus frequency of scattered. Or in wave number form, delta mu bar is equal to mu I bar minus mu S bar. For Stokes lines, Raman shift is positive, we already discussed. And for anti-Stokes lines, Raman shift is negative. Then that Raman shift is nothing but equal to energy difference between two energy states of that sample or that matter. That matter consists of different energy states, and energy difference between that two successive states is nothing but E2 minus E1, that is nothing but delta E, which is nothing but Raman shift, responsible for Raman shift. That Raman shift is characteristic property of scattering material. Therefore, like fundamental frequency of vibration, it can be used for identification of samples. That is for rotational Raman spectrum, Raman shift is found to be of the order of 100 to 250 centimeter inverse, and for vibrational rotation spectrum, Raman shift is of the order of 1000 centimeter inverse. This is about that Raman shift. Then here we stop now. Thank you.